Today we're going to head into an introduction for vectors in 3D, and I'm going to talk about all the admin things you need to know before heading into the questions proper. So some admin stuff, the first thing about vectors you need to know is the notation. So most vectors, right, are either expressed as small letters, point to point, or when you go into your workings in the form of x, y, z stacked up as so. So for small letters, you would have, like the first page, you would have the small letter with an arrow on top or small letter with a tilde below. Right, so we call the squiggly line and tilde, so it's either this or this, but for H2 mathematics, we most commonly use this. Right, and point to point, we have, let's say it's from point A to point B as a vector. We have AB with an arrow on top, right, pointing to the right because it's moving from A to B, and the arrow always points to the right. So make sure your points are always moving from O to X, right, from maybe B to C, BC. Right, and the third kind of vector notation would be 3 elements stacked up as so, and I'll explain why later. We can have maybe 1, 2, 3, maybe -1, half, 3. Right, but essentially what this means is that we have -1 units in the x, half units in the y direction, and 3 units in the z direction. Right, so what are vectors actually? Now in the past we learned about Cartesian, the Cartesian graph over here. So let's say when we have a point 3, 4, right, 3, 4, what you're doing is you're actually moving 3 units in the x direction and 4 units in the y direction as so. Right, so in vector form this will be expressed as 3, 4. Right, this point will be expressed as 3, 4. It's a direct movement from O to the point. Right, so this vector will be expressed as 3, 4 in the Cartesian form. But now with 3D vectors, right, moving straight to 3D vectors, we have a third axis called z. So imagine it's moving into the page, z. Right, and let's say we have a point 1. Let's say we have point 1, 2, 3. Let's choose this point. Right, you're moving 1 unit in the x direction, 2 units in the y direction, and 3 units in the z direction, right? So imagine a point that's floating in midair, right, into the page, and it's over here. So let's say we have P, right, and in the coordinate form we have 1, 2, 3, or in another case, we call this a position vector OP, right? O moving to P is equal to 1, 2, 3. So we have position vectors are equal to the when you say we have a position vector of the point P, right, the position vector refers to the vector moving from O to P. Right, so let's say we have another point over here, maybe let's call it Q. Right, the position vector of Q, so it's always a position vector of a point. The position vector, right, in inverted commas, of Q. Right, so this term will always come out in questions. Position vector of Q would be equal to OQ, with an arrow pointing to the right on top. For operations, I won't go into much detail because we can talk about that later, but for operations we mainly have addition of vectors. So let's say we have 1, 2, 3 plus -1, half, 3, right? Essentially, when you add two vectors, or let's say 1, 2, 3, you add up all the elements in the x direction and in the y direction. So that's 1 plus -1, we have 0. 2 plus half, we have 2.5, and 3 plus 3 we have 6. So the resultant vector is 0 units in the x direction, 2.5 units in the y direction, and 6 units in the z direction, right? So the resultant vector can be formed by addition, subtraction, and what you have. So the first operation would be addition or subtraction. All right, and the second operation is not multiplication, it's scalar multiplication. All right, so this is a really special term in vectors. We call it scalar. And all it means is that you're scaling the vector. So let's say we have a vector of 1, 2, 3, right? So we want to scale it by 2 times. All you need to do is to multiply it by 2. Right? And we call this number over here a scalar multiple, right? Because it literally scales the vector. And, well, there's no scalar division, but if you want to divide it by 2, so you want to divide it by 2, all you need to do is to multiply it by half. Half times 1, 2, 3. Right, and this is also called a scalar multiple. So these two things are lumped under what we call scalar multiplication. Right, and for the last two types of operations, we're gonna touch it. We're gonna go into way more detail later on. Right, so the first kind would be scalar product. Right, it's represented by a dot. So the scalar product of two vectors u and v, right, would be u dot v. Right, so this dot is called a dot product or scalar product. Right, we're going to use it a lot later on. Dot product or scalar product. Right, and finally we have the vector product. Right, and the vector product of two vectors u and v would be equal to u cross v. Right, so it looks like a times, but it's called cross. So we call it the cross or vector product. A really useful property derived from the position vector. So just to recap, a position vector is the vector moving from the origin to a point. So let's say we have points OA and B as well. Right, the position vector of A would be OA, and the position vector of B would be OB. Right, defined by OA or OB. Right, and the property that you can derive from this is AB is equal to OB minus OA. Right, and how I got this is that now let's say we want OB to be the resultant vector. Right, when we have OA plus this vector over here, we can reach point B. Right, so the thing about vectors is that when you add a specific vector, you're moving from that, or you're moving from the initial point to that vector. Right, so when you have OA, right, you're moving from the origin to A, and when you add AB, so we have OA plus AB, right, you move from A to B. Right, so adding a vector is as simple as moving along the vector added. And you arrive at point B. Right, so when you arrive at point B, this particular point has the position vector OB. So OA plus AB is equal to OB. Right, and just by rearranging, we have AB is equal to OB minus OA. And how I remember this property is the vector in question, so AB, right, you take the right letter position vector minus the left letter position vector. So it's always right then left. The magnitude of a vector is exactly the same thing as the modulus of a vector. So the magnitude of, let's say, PQ, for example, right, is directly related, right? Actually, it's the same thing as the modulus of PQ. The modulus of PQ, and it's exactly the same thing as the distance PQ, or the distance from P to Q. Right, when we say the distance PQ, we don't put an arrow on top, right? It's just empty on top because it's the distance from one point to another point, right? There's no vector involved. And the magnitude of PQ is defined by, or rather the notation is PQ with an absolute value at the side. So this is the same thing as the magnitude of the three vectors. So let's say PQ is equal to, let's say 311, right? The magnitude of 311, you write it like that. And it's also equal to the magnitude of OQ minus OP. Recapping our previous property, right side letter minus left side letter's position vectors. Right, so PQ is equal to OQ minus OP. Okay, so how you compute the modulus is you take the square root of the sum of the squares of the individual components. So when we have 331, right, it's 3 squared plus 3 squared plus 1 squared. Now you derive this using the Pythagoras theorem, and let me show you how. So this is equal to square root 19. So the distance from P to Q is equal to square root 19. So onto the Pythagoras theorem. Okay, let's say we have a point x over here, which is 3 units in the x direction, 3 units in the y direction. Essentially, OX is equal to 3 squared plus 3 squared, and root of that, well, you get root of 18. So when you have the root of 18, now I'm going to introduce to you an additional point, which is the z-axis. Bad color. The z-axis is into the page. Well, just imagine it's into the page. And you have a point over here, which is traveling parallel to the z-axis. So it's into the page is 1 unit into the page. So we have a point over here called maybe y. Right, so you've already figured out the the distance OX, and imagine that this point is into the page, right? So it's essentially it's perpendicular. It's perpendicular. I don't know if you can visualize it, but it's perpendicular. So if you look from the side, so let's say I'm looking from the right side now. I'm looking from the right side. I have OX, and I'm moving 1 unit into the page, right? With Y over here, and this is root 18 as calculated. So the length of OY is equal to the square of root 18 plus 1 square, whole thing root, by the Pythagoras theorem, and that's equal to root 19. And you realize that the length of the sides that I use is the same as this vector over here, because it's moving 3 units in the x direction, 3 units in the y direction, and 1 unit in the z direction. So essentially, in summary, the modulus of a vector is equal to the square root of the sum of these individual squares. The unit vector of a vector, now let's say unit vector of OX, right? With this vector is represented by small x with a tilde below. So the unit vector of OX is equal to, now the unit vector is represented by small x with a tilde below and a roof on top. So this roof represents the unit vector. Now it's really important to derive the unit vector. The applications will come later on, but most important is to understand why we need this unit vector. So let's say we have a long vector over here, right? From moving from O to X, where OX is equal to, let's say 3 plus 5 plus root 2. So it's 3 units in the x direction, 5 units in the y direction, and root 2 units in the z direction. Now we know the magnitude of OX, or the magnitude of x with a tilde below. Right, these are equal to the square root of, now, x component squared plus y component squared plus z component squared, right? Given by the Pythagoras theorem. And that's equal to the square root of 9 plus 25, that's 34, plus 2 is 36. And that gives you 6 units. So you know the magnitude of this thing is 6 units. So let's write that down, 6 units. Right now I want to know what's OX but 1 unit. So it's moving in the direction OX, but I want to know what it's like when it's 1 unit in magnitude. So let's say this point Y over here. I want to know OY, where OY has the magnitude of 1 unit. Right, and one way to do it is to divide OX by 6. So we have OY is equal to 1/6 of OX, because it's moving in the x direction, OX direction, but it's only 1/6 of the magnitude. So that's 1/6 times OX, and that gives you 1/6 of 3, 5, root 2. Now this is really important later on, because this is literally like the base Lego block of all the vectors. Now the ratio theorem, which is a property that comes from the position vector property, right? The properties and proofs eventually help you with the application. So understanding how they're derived is super important. The ratio theorem is given by 3 points, O, A, and B. OA has position, A has position vector small a tilde below. OB has position vector small b with tilde below. Right, OA, OB. And we also have a point M, which divides AB in the ratio of lambda to mu. So this point M, right, we have AM is equal to lambda over lambda plus mu, the whole length of the line's units, right, times AB, right? So AM is just this small segment of the whole AB. And this ratio theorem is about finding the position vector of M. So can you see how I'm going to do it? Now, the position vectors eventually help you split these vectors over here into position vectors, because these are the only variables you can work with, A, lambda, mu, and B. And how you're going to do it is you're going to split the left hand side and the right hand side into the individual position vectors, because you want to make small m the subject of the equation. So on the left hand side we have, so going back to our position vector formula, we have the right hand side letter minus the left hand side's position vectors. So it's small m minus small a is equal to lambda over lambda plus mu times small b minus small a, right? Because the right side letter minus left side letter's position vectors. And now I'm going to add a to the other side, so I've successfully made m the left hand side of the subject. So it's Now I'm going to combine the fractions. A times that, whole thing over lambda plus mu, plus lambda times b minus a. Now the a times lambda cancels out with this lambda a over here, and all that's left is m is equal to a times mu plus lambda times b over lambda plus mu. Right, so essentially how this looks visually is a is multiplied with mu, b is multiplied with lambda, right, and the whole thing is divided by lambda plus mu. So now let's give some values. So let's say we have a is equal to 1, 1, 1, something easy to work with. B is equal to maybe negative 1, 2, 0. Right, and m divides AB in the ratio 1:2. Find the position vector of m. Now, all we have to do is to plug in the formula. So we have OM is equal to, now what's A times mu? A is equal to 1, 1, 1, right? We have 1, 1, 1 with mu is equal to, what's mu equal to? Mu is equal to, in this case, A divides AB in the ratio 1:2. So lambda is equal to 1 and mu is equal to 2. So A is multiplied by 2. And we're going to multiply it by, add lambda b. So b is equal to negative 1, 2, 0. And we have lambda is equal to 1. So multiply by 1. Whole thing over lambda plus mu. So that's 1 plus 2. And that's equal to 1/3 of, what do we have? We have 2 times 1, 1, 1. That's 2, 2, 2. Right? Plus negative 1, 2, 0. And this gives us 1/3 of 1, 4, 2. So we successfully found that the position vector of point M has these, has these values, is this value. Right, so the ratio theorem is kind of complicated with this formula over here, but the idea behind it is really simple.